Hello everyone, I am Lokendra. I am chemistry faculty at Toppers Academy. In today's class, I will discuss all the topics of the chapter atomic structure. Okay. So for your convenience, I am going to divide this chapter into 4 parts. So in today's class, we are going to deal with the chapter atomic structure. I'm going to divide this whole chapter into 4 parts. Okay. In first part, we will see the subatomic particles. Okay. In the second part, we will see all the atomic models that are present in this chapter. Okay. In the third part, I am going to discuss development towards quantum mechanical model. Okay, it is the development towards quantum mechanical model, and in the last part I will discuss quantum mechanical model. Okay, so I'm going to start the first part of this chapter, atomic structure. Okay, so in the first part of this chapter, that is subatomic particles, so we see that which and what type of subparticles are present in an atom, right? Or an atom, what types of particles are there present. Okay, so in an atom there is a nucleus at the center of atom, in which neutrons and protons are present, and around the nucleus electrons are present. These electrons revolve around the nucleus. Okay, the charge on electron is -1. I am going to write here charge. Okay, and here I am going to write about mass. Okay, so electron -1 charge, proton +1 charge, neutron are neutral, right? Mass of electron is 9.1 into 10 to the power -31 kilogram, and mass of proton is 1.674 into 10 to the power -27 kilogram. Mass of neutron is 1.67, actually it is 1.672 for proton, and 1.674 into 10 to the power -27 for neutron. Okay, so if you see the mass order for these subatomic particles, so we will observe that the mass of neutron and proton is similar, right? But it is 1.674, it is 1.672, right? So mass of neutron is greater than that of mass of proton, right? And if we compare neutron, proton, electron collectively, you will see that the mass of electron is least in all these 3 subparticles. Okay, so it is the order of their mass, right? And I am going to tell you about the atomic mass unit value. It is 1.661 into 10 to the power -27 kilogram. Because these are very complex values, so we cannot use in a very easy way, so we will provide another form of mass, in which it is another unit of mass, we can say that AMU, right? For our convenience we use AMU, right? So I am going to write here mass in AMU, right? Mass in AMU. So what I will do, I will divide this 9.1 10 to power minus 31 kilogram. I will divide this value also. I will divide this value also by 1.661 into 10 to power minus 27 kilogram. So when I divide this 9.1, the mass of electron, 9.1 10 to power minus 31 by 1.661 10 to power minus 27, I will get the value of 0.00548. When I will divide 1.672 by 1.661 10 to power minus 27, I will get the value 1.007 AMU. It is 1.008 AMU, right? 1.007 and 1.008 AMU. It is in AMU, it is in kilogram, right? And in this topic, we also deal with some more basic terms, like what is the representation? What is the representation of an atom? We also deal with that. So representation of an atom, that means how we represent an atom, right? So the representation of an atom is like that, X, right? And here we write atomic number Z, here we write atomic mass A, okay? Atomic number and atomic mass. What is atomic number for an atom? Atomic number is the number of protons in that atom, right? Number of protons. What is the atomic number? Actually Z is atomic number, and atomic number is equal to the number of protons in that atom, right? And what is A? It is atomic mass. Atomic mass is equal to the number of neutrons and protons in an atom. So I can write atomic mass is equal to number of neutrons plus protons. So see here, I can write this as X, number of Z is equal to P. So I can replace Z by P. I can replace A by N plus P, right? So how we represent an atom? We represent X, right, in subscript. On the left side it is subscript. These both positions are known as subscript, and this position is subscript on left side. So subscript on right side we write atomic number. In superscript on left side we write atomic mass. We represent atomic number by Z, we represent atomic mass by A, and atomic number Z is equal to number of protons for every atom, and value of atomic mass is equal to the number of neutrons plus proton. So this is also a chemical representation, right? So this is how we represent an atom, okay? Now see that some more basic terms. So let me tell you two basic points, that addition of an electron in an atom will make negative charge on an atom. Negative charge, that means atom will be now anion, it will be anion, right? And removal of an electron from the valence shell or from an atom leads to the formation of positive atom. That means it will have positive charge and it will be a cation, okay? Now we deal some more basic terms in this part, that is we are dealing now some subatomic particles, right? We are dealing now some subatomic particles, right? So see, we deal also with isotopes. What are isotopes? Which have same value of atomic number. Same atomic number. For example, 6C12 and 6C14 isobar, same atomic mass. That for example 6C14 and 7N14. Okay. Isoelectronics, same number of electrons. For example Na and Ne. In the current scenario there are 10 electrons in Ne and 11 electrons in Na, because the atomic number of Ne is 10, atomic number of Na is 11, right? But if I remove one electron from this, there will be 10 electron and there is already 10 electrons. So these are the examples of isoelectronic, right? Now I am going to discuss with the another term, isotones or isoneutronics. Okay, isotones or isoneutronics, that means same number of neutrons, same number of neutrons. For example 1H3 and 2He4. So see, 3 minus 1 there are 2 neutrons, 4 minus 2 there are also 2 neutrons. If we want to calculate the number of neutrons in an atom, so generally we subtract atomic number from atomic mass, right? So this is how that we have discussed basic terms. We have discussed about the representation of an atom, subparticles, right, subatomic particles. Now I am going to deal with the another next term, that is atomic models, right, in the next slide. Okay, atomic models. Right, atomic models. So see, initially the initial model was Thomson model, that we generally know, Thomson model, right, Thomson model. So it is also known as plum pudding model, right. So what he said that he compares an atom with watermelon. He says that as plums are present in watermelon, similarly in atom there are electrons present, right. So suppose it is a watermelon and these are the plums which are present. Okay, so he said that in the similar way these plums are, he compared that these plums are electrons in case of atom, and this pudding part that we eat, red part, is the positive charge spread out in all the space of atom, right. So this is Thomson model, right. Now I am going to deal with the next model. It is Rutherford model. Right. So Rutherford model. See what he did. He bombarded alpha particles on the thin layer of gold, right. So let me tell you what is the alpha particles. So there is a helium atom 2He4. I am going to tell about alpha particle. There is a helium atom 2He4. In this atom there are number of protons 2, number of electrons 2, number of neutrons 2. 2 number of neutron, 2 number of electron and 2 number of proton are present in 2He4, that is helium atom, right. So let me show it diagrammatically. So number of protons and neutrons, number of neutrons and protons are present here. Number of neutrons and protons are present here. So I am going to write here, represent number of neutron, that is 2, number of proton, that is 2, 2 protons, 2 neutrons, and here 2 electrons. Here 2 neutrons and 2 protons are present in the nucleus, and around the nucleus there are 2 electrons, right. So if we remove these 2 electrons one by one, if we remove, there are only 2 electrons, and I am going to remove all both of these 2 electrons from the outer shell, right. So see what will happen, there will be only nucleus left, right. So in which 2 neutrons plus 2 protons will be present, because 2 electrons were around the nucleus and I have removed these 2 electrons. So what will be left? Only nucleus, okay, in which 2 neutron and 2 proton will be present, and we know that neutrons are neutral and proton is having +1 charge, right. So 2 proton will have 2 plus charge, so that why we say that alpha particle have +2 positive charge, right, because 2 neutron will have 0 charge because neutron is neutral, and because of 2 proton there will be +2 charge. So overall +2 charge is present on the nucleus of helium atom, and this nucleus of helium atom is generally known as alpha particle, right. So we represent it as 2He4, 2 plus charge here. This is the nucleus of helium atom. Why I am saying it as nucleus? Because the electrons has been removed, all the electrons has been removed, so there is present only nucleus now, right. So that's why I am saying it as nucleus, right. So 2He4, 2 plus charge, we say it as alpha particle and it has +2 charge. So that means alpha particle is positively charged particle, okay, positively charged particle. Rutherford model. So what he did, he bombarded alpha particles which are positively charged particles, and he gave some postulations. He said that because most of the particles passed away without any reflection in their angle, so he said that most part or space is empty in an atom, right. And one more thing, he said that the positive charge is not spread out in all the space in an atom, it is present in a very small volume in an atom, right. He said that positive charge is not spread out, positive charge is present at very small volume or space in an atom, right. So this was Rutherford model. Next is Niels Bohr model, but before Niels Bohr model, let me discuss Planck's quantum theory, because he used this theory and gave his model, right? So what is the Planck's quantum theory? Planck's quantum theory is Planck's quantum theory. He said that a system can absorb or emit energy of discrete level, right? He gave the formula E is equal to h nu or E is equal to hc upon lambda, because nu is equal to c upon lambda. So we can write that E is equal to hc upon lambda also, because nu is equal to c upon lambda, where h is Planck's constant, whose value is 6.6 into 10 to the power minus 34 joule second. C is speed of light into 10 to the power 8 meter per second, and lambda is wavelength, right? So E is energy. So he said that a system can absorb or emit energy in discrete level. Okay. So using this using this theory, Bohr gave his model, Bohr's model. He said that, Bohr said that there are many orbits around the nucleus. There are many orbits around the nucleus which have fixed radius and fixed energy, right? Fixed radius and fixed energy of orbits, right? Okay. He said that when the angular momentum of an electron which revolves around the nucleus is equal to angular momentum, it is equal to m. See, m is mass. If I multiply it by velocity, it is now momentum, and if I multiply it by radius of the orbit in which electron is revolving, now it is angular momentum, right? If a particle moves in a linear direction, so we use momentum, mv. If it moves around something, or I can say that in a circular orbit, then we do not use momentum, we use angular momentum in this case also, right? Angular momentum, mvr is equal to nh upon 2 pi. Why I am using here angular momentum? Because electron is revolving in a circular orbit, circular path is here, right? So mvr is equal to nh upon 2 pi. So these are the models, atomic models, which are present in this chapter, right? So Rutherford and Neil Bohr model is generally important, because Thomson model is very general and all know about this Thomson model, right? So I am going to discuss with the next topic. So what we have discussed till now, see, we have discussed subatomic particles, we have discussed about atomic models. Now I am going to discuss with you development towards quantum mechanical model, in which we will deal with two sub parts, right? First is, it is this topic I am going to discuss, development towards quantum mechanical model. In this part I am going to discuss about another two subparts. It is development towards quantum mechanical model, right? In this part I will discuss two subparts, which are, let me change the color, which are Heisenberg uncertainty, Heisenberg uncertainty principle. So he said that if an electron is revolving around a nucleus in an atom, that it is not possible that you can calculate position and velocity of that electron simultaneously. If you do so, you will have an error. Okay. So for an electron, we cannot calculate position, value of position and velocity simultaneously. Okay. So the error in, if you do so, you will have error. If error in position, actually we represent position as small x and error in position as small as delta x, delta x, right? Del x del p is equal to or greater than h upon 4 pi. Okay. So what he says that position and momentum cannot be calculated simultaneously. Right. One more thing. It is delta x into delta p is equal to or greater than h upon 4 pi. And I have told you that momentum, I can write momentum as mass into velocity, mv. So I am going to replace p by mv. So see, mass is always constant, it do not change, it will not have error. So I can rewrite here position and momentum or velocity. I will discuss it later. So it will be delta x into delta v is equal to greater than h upon 4 pi and m will be now in denominator. I can rewrite it as also like that. So see, we can say that position and momentum cannot be calculated simultaneously, right? Or we can say that position and velocity cannot be calculated simultaneously. We cannot say that position and mass cannot be calculated simultaneously. Actually, mass we have calculated, I have discussed it later, that mass of an electron is 9.1 10 to power minus 31 kilogram. So how I can use mass? It is fixed, right, for an atom, for an electron. The another term that we discuss here, it is Heisenberg uncertainty principle. It is dual behavior of matter. It is dual behavior of matter, right? So according to this, it is de Broglie, the scientist who gave this dual behavior. So according to this, if an object, particle, small particle or bigger object, so an object have two types of nature in it, particle nature and another is wave nature, right? Particle nature and wave nature, dual behavior. That means two types of behavior, that is particle behavior and wave nature, wave behavior, you can say that. So because of particle nature, you can write E is equal to mc square, because if it is a particle, it will have mass. And because of wave nature, E is equal to h nu or hc upon lambda according to Planck's quantum theory. So in the left side, both of these equations have capital E. So obviously right side will be also equal. So I am going to write as mc square is equal to hc upon lambda, because both of these equations are equal. They have equal left side, so obviously I can equate the right side of these equations also, right? So now it is mc is equal to h upon lambda. Is saying that m proportional to 1 upon lambda. You can replace here c, that is velocity of light, by v. You can write it as mv is equal to h upon lambda. So in books or in another cases, mv is equal to h upon lambda, you can find it also, right? So m, according to this, m proportional to 1 upon lambda, because speed of light is constant and h is Planck constant, the value for these two part is constant. So I can write m proportional to 1 upon lambda. So according to this dual behavior of matter or de Broglie equation, it says that if higher the mass, lower will be lambda, right? Higher the mass, lower will be lambda, and lower will be the wave behavior or wave nature, right? If an object has lower mass, it will have higher lambda and it will show higher wave nature in it, right? High wave nature. High wave nature, or here low wave nature will be observed. Low wave nature. Low wave nature, it is low. Low wave nature. Oh, 1 second. Low wave nature. It is high wave nature. So if an object of higher mass, it will have lower lambda, so obviously it will show low wave nature. So suppose I am taking here an example. Suppose there are two types of object I have. There is a stone and there is electron or atom or molecule, right? So these have very minute mass. So this stone has high mass as compared to the mass of electron. It is having lower mass. So stone has high mass. If high mass, so lower will be lambda and lower wave nature. So it will show low wave nature. And electron is having lower mass, so it will show high wave nature in it, right? So higher the mass, low wave nature or low lambda, or lower the mass, high wave nature. So electron have very less mass, that is 9.1 10 to the minus 31 kilogram. So it will show high value of lambda. So it means it will show high wave nature. So we cannot neglect the wave nature of electron. We can neglect the wave nature of stones, of particles, of ball. We can neglect the wave nature. But in case of electrons, atoms or molecules, the wave nature is high. We cannot neglect it, right? So this is the third part that I have discussed. Development towards quantum mechanical model. So based on these these subparts that I have discussed, that is dual behavior of matter and the Heisenberg uncertainty principle, based on these two subparts, the quantum mechanical model is based. is formed, right? So now I am going to deal with the last part of atomic structure chapter. It is quantum mechanical model, right? So quantum mechanical model. Quantum mechanical model, right? Quantum mechanical model. First of all, I am going to tell you the what is the meaning of mechanical or mechanics, from where this word has come, right? Mechanics. What is the meaning of mechanics, right? Okay. Mechanics. What is this? Actually, it is a branch of science which deals with the motion of objects. It is the branch of science which deals with the motion of objects. I am going to write here. Branch of science which deals with the motion of objects, right? Okay, now I am going to divide it further. I am going to divide this branch, mechanics, right? Mechanics. Classical mechanics, and quantum mechanics. Classical mechanics and quantum mechanics, right? So it deals with the motion of macroscopic objects which has higher mass. For example, stone, planet, etc. It is based on Newton's laws of motion. This is classical mechanics, right, which based on the Newton's law of motion, and it deals with the motion of macroscopic objects. Macroscopic objects has higher mass, like stone, like ball, like mobile phone, right? So anything which has high mass. And this quantum mechanics, it deals with the motion. We apply quantum mechanics for calculated or for knowing about the motion of microscopic objects like electron, proton, neutron. Actually, proton is present at the nucleus. It is present at the nucleus. It is not revolving, right? So we can apply quantum mechanics for knowing the motion of microscopic objects like electron, atoms, or molecules, etc. Okay. It is based on dual behavior of electron of matter, for which you are applying quantum mechanics. Electron, atom, or molecules, right? What you will have it will consider it as that it will have two types of behavior. Suppose you want to calculate the motion of electron in an atom. So it will consider that this particle, this electron will have two types of behavior, that is particle nature and wave nature, right? Suppose you want to know the motion of microscopic object, that is atom. So it will consider that atom will have two types of behavior, that is wave nature and particle nature. Similarly, if you want to apply for the motion of molecule, so it will consider that this molecule will have two types of behavior, that is wave nature and particle nature, right? So what is the name of our chapter? It is atomic structure, atom, atomic structure, atom. So atom is a microscopic object, so we apply quantum mechanics here because it is a microscopic object. We cannot apply here classical mechanics, we cannot apply this here, okay? So that's why we have discussed the dual behavior of nature, because it comes under quantum mechanics. We cannot apply here Newton's law of motion, because these small particles have high wave nature. So wave nature cannot be neglected, and in case of classical mechanics, in case of Newton's laws of motion, the wave nature has been neglected, but you cannot neglect here, okay? So we are going to have some more idea about quantum mechanics, right? Quantum mechanics. This quantum mechanics was introduced by two scientists, Schrödinger and Heisenberg. These two scientists introduced this quantum mechanics, but the fundamental equation was given by Schrödinger, for which he was awarded by Nobel Prize, okay? Schrödinger. So Schrödinger equation H psi, okay, is equal to E psi, H cap psi is equal to E psi, okay? What is psi? Psi is wave function. What is H? It is Hamiltonian operator, mathematical operator it is, and E tells about the energy, total energy. So listen, suppose we have a wave function. If we apply Hamiltonian operator on that wave function, then we will get the value of energy regarding that wave function, okay? If we have a wave function psi and we apply Hamiltonian operator on that function, we will get the value of energy, okay, right? Now let me tell you what is the wave function. Let me tell you what is the wave function. See, what is the wave function? What is the wave function? Let me tell you that. See, if there is a straight line, we can represent it mathematically by y is equal to mx plus c. If there is a straight line, so we can represent it as y is equal to mx plus c. Y is equal to mx plus c. If we have a circle, parabola, hyperbola, we can represent these type of structure mathematically by a single equation, right? Any shape can be represented mathematically by a equation, right? It is a mathematical representation of that structure or of that shape. Okay. Similarly, in an atom, suppose electron is present in this space. Suppose in an atom it is a nucleus and around it is there is a orbit, and in this orbit electron is revolving, and suppose in this space the electron is present, right? So this space is represented by wave function. The space in which electron may be present or is present, that space is represented by wave function mathematically. It is mathematical representation of the space in which electron may be present. Okay. So wave function represents the space in which electron may be present or has the maximum probability of finding, right? Okay. And generally this space in which the probability of finding the electron is maximum, this space is known as orbital, and this orbital generally known, we can say it as atomic orbital because it is orbital of atom, so atomic orbital. So this is atomic orbital in which electron may be present. You can say that it is a house of an electron that in which electron may be present, right? So this house, the structure of this house mathematically is represented by this wave function. I have said that every structure can be shown by a mathematical representation. So similarly, the shape of or the representation of the space, that is orbital. What we call this space in which electron may present? Orbital. It is the house of, you can say that it is the house of an electron. So the representation of this house is given by the mathematical function, by the wave function psi. Okay, this is. Now this Schrodinger wave equation gives three types of quantum numbers, three types of quantum numbers, that is N, L, M, right? Actually this wave function has the information of the orbital in which electron may be present, and for that orbital it gives three quantum numbers N, L, M, by which we can have idea about that orbital, right? So we will see that what are these quantum numbers. I have discussed that from where the quantum numbers has come out, right? So say quantum numbers. Listen carefully. Wherever you are living at the right moment, you have your proper address. Suppose this is the city in which you are living at the current moment. In that city, it is the colony in which you are present, right? In that city, this is the building in which you are present. In that building, this is the floor where you are present right now. You have your proper address. Okay. Similarly, in an atom, there are a lot of electrons present. These electrons have their particular position, their particular energy value. Okay. So the position, so what I am saying that you have address for your location and the electrons have quantum numbers for their location. Similarly, okay, if I want to go, if your friend want to go to your home, so you will have to tell your address to your friend so that your friend will go to your home, right? So similarly, if I want to know, if I want to talk about the particular electron in an atom, so first of all I will have to know what are the quantum numbers of that electron in an atom, right? So see, quantum numbers tells about the position and energy of electron in an atom. Whatever. Okay. There are 4 types of quantum numbers. There are 4 types of quantum numbers. One is n, principal quantum number. Number 1 is principal quantum number. One is principal quantum numbers. Another is L. It is azimuthal quantum number, or we call it as subsidiary quantum number also. Third one is magnetic quantum number, which is represented as small m. Fourth one is S, spin quantum number. Okay. It tells about the shell. Size of orbital, okay, it tells about shell and size of orbital. Okay, see what is the meaning. What is orbital? It is the house of an electron in which electron may be present, or we can say that the probability of finding that electron is maximum at that space. Generally, it is approximately 90%. So, if the size of house, suppose it is n is equal to 1, it is first cell. It is n is equal to 2, it is second cell. Generally, we call it if it is n is equal to 3, it is third cell. Right. Generally, we call it K. It is as L. It is M, and fourth is called as N. K, L, M, N. Right. So suppose there is a orbital in the first shell. Suppose there is an orbital in the first shell and there is a orbital in the third shell. The size of the orbital of third shell and the size of the orbital of first shell can be compared, because higher the value of n, higher will be the size of orbital. Higher the value of n, that means principal quantum number, higher will be the size of orbital. That means the size of orbital of n is equal to 1 shell will be lesser than the size of orbital of n is equal to 3. Okay. Now listen. Number of orbital, we can calculate number of orbital also here. It is equal to n square. N square is equal to the number of orbitals for that particular cell. That means if n is equal to 1, so orbitals will be only 1 square, that means 1. If n is equal to 2, so number of orbitals will be 2 square, that means 4. If there are n is equal to 3, that means the number of orbitals will be n square, that means 3 square, that means 9. Okay, it means first cell only 1 orbital, second cell have 4 orbital, 1, 2, 3, 4 of bigger size, because n is equal to 2. As n is equal to 3 has 9 orbitals, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. What is the orbital? Orbital is the house of an electron. We can say that it is the space in an atom which has the maximum possibility of finding the electron. Generally, this probability or possibility is 90%. So see, azimuthal quantum number, it tells about subcell. It gives information about the subcell. If L is equal to 0, 1, 2, 3, then subcell will be S, P, D, F. So I am talking about here subsidiary quantum number, that is small l. We call it as azimuthal quantum number also. Okay. It also tells about the shape of orbital. Azimuthal quantum number also tells about the shape of orbital. What is orbital? It is the house of an electron. And what is the information getting here? We are getting here. What is the shape of that house in which electron may be present? Okay. So L value decides what is the shape of that orbital, but N value will decide what is the size of that orbital, right? Actually, there is a difference between size and shape. So listen, it is a rectangle, it is also a rectangle, both have same shape, that is rectangle, but both do not have same size. One is bigger, one is smaller. Suppose there is a rectangle, this is a triangle. Both have similar size, but both do not have same shape, because one is rectangle, one is triangle, but they have similar size. Okay, so there is a difference between shape and size. So about size, we got this information from N. About shape, we got the information from L. Okay. Now I am going to tell about the magnetic quantum numbers M. It tells about the orientation of orbital in 3D. That means orientation, possible orientation. I will discuss it later. The value of M is equal to 2L plus 1. Its possible values are from minus L to plus L, minus L to plus L. So value of M is to L plus 1. It is let me take an example. Suppose L is equal to 2. So possible values of M will be equal to minus 2 plus 2, that means minus 2 minus 1 0 plus 1 plus 2, and according to this formula this must be 12 plus 1, that means 2 into L, value of L is 2 plus 1, that means it must be 4, and it is also here 4, 5, it must be 5, it is 1 2 3 4 5, right? And what is the meaning of this orientation, right? What is the meaning of orientation? Suppose the value of M, magnetic quantum numbers, which is telling about the orientation, the value of M is 3. So it means it can have 3 types of orientation, like this type of orientation, this can have this type of orientation, this can have this type of orientation, right? So it will tell about the possible orientation. Okay, spin quantum numbers. Actually, likewise Earth spins around its nucleus also, right? So similarly electrons, when an electron, suppose the electron is revolving around the nucleus in a circular way, it is at the same time it is also revolving, it is also spinning around its own axis, right? Its spinning may be of 2 types. One is clockwise, which is generally represented by up arrow, and anti-clockwise. It is the value of spin quantum number for clockwise direction is plus half, for this it is minus half. Okay, so that is, I have discussed about the quantum numbers. Now I am going to take some examples that how we calculate quantum numbers, right? I will take 4 examples here and I will calculate the quantum numbers, 4 quantum numbers for each example. Let me take, suppose there is a question, calculate quantum numbers for 4s1. Suppose it there is a 3d3. Suppose there is example of 4p3, there is example of 4f8, right? SPDF. I have taken 4 different type of examples, right? Now I will calculate the value for NLMS, that is, these are the quantum numbers. So see, actually what is the meaning of 4s1? That means we have to calculate the value of quantum numbers for the electron which is present in the s subshell of fourth shell. We have to calculate the value of quantum numbers for the third electron which is present in the d subshell of third cell. We have to calculate the quantum numbers for the third cell which is present in p subshell of fourth cell. We will have to calculate the value of eighth electron which is present in the f subshell of fourth shell. Right. Now I will discuss it. So the first of all I will write here value of L 0, 1, 2, 3 of 1 second. Subcell S, P, D, F. Value of L will be 0, 1, 2, 3. Number of orbitals that may be present. Here 1 orbital, here 3 orbitals may be present, here 5 orbitals, here 7 orbitals may be present. Number of electrons. So listen, one orbital can have maximum 2 electrons. So the value of electrons for one orbital will be 2. It's just double. 6, 10, 14. Right. So the value of n is equal to 4. Actually, the value which is written in the first, it is taken as a value of n. That means it is talking about the fourth shell, and value of L, it is S. So S, that means value of L will be 0. Now I am going to talk about the orbitals. So how many orbitals will be there? Only one orbital. Only one orbital will be there. So the value for this orbital is minus L2 plus L. That means minus L2 plus L, and the value of L is 0. That means minus 0 to plus 0. That means 0. Right. Possible value of n is equal to 0. And only one electron. If one electron is present, we make it as clockwise in up direction. And for this, the value of m is 0, and for this we consider it as it has clockwise direction, so we will take the value as plus half for this. Okay, now I am going to take the another example. It means it is talking about third shell, so n is equal to 3. D subshell, and for D subshell the value of L is equal to 2. So L is equal to 2, and the possible values of, so how many orbitals will be here? 5 orbitals. I will make 5 orbitals. So orbital is represented as just boxes. And what is the orbital? Orbital is the space in an atom in which electron may present. That means it is the house of an electron. So the possible values of m is equal to minus L2 plus L. That means minus 2 to plus 2, because the value of L is equal to 2 here. So minus 2 to plus 2, that means minus 1, 0, plus 1. Now I will fill here 3 electrons, 1, 2, 3. So for this electron I am going to tell about. So the value of m will be 0. Value of S will be plus half, because it is clockwise, it is present in up direction. So these were the possible values of m, but out of these 5 possible values, only m is equal to 0 is suitable for the third electron, for this electron. Right. Now I am taking another example, that is n is equal to 4, L is equal to SP. For P it is 1, N, L, M. So how many orbitals will be there? 3 orbitals, right? For P subcell, 1, 2, and the value of M is minus 1, 2 plus 1. So 0 will be in between. So I am going to fill 3 electrons here, 1, 2, 3. So we will have to calculate the value of M for this electron, that means it is plus half. So out of these 3 possible values, plus 1 is for third electron which is present in the P subcell of fourth cell. S is plus half because it is in the clockwise direction. Okay. Now I am going to tell about the last example. N is equal to 4. N is equal to 4 here, because this value tells about the N value, and L for F subcell, F value of L is 3. It is a value of L, right? And for this case I will have to draw here 7 boxes, that means 7 orbitals, that means 7 houses of electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So the possible values are minus 3, minus L2 plus L, minus 3 2 plus 3, minus 2, minus 1, 0, plus 1, plus 2. There are 8 electrons, so I am going to fill 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Right, 8. So the last electron is present in this orbital, for which M is equal to minus 3. So S will be, it is down, it has anti-clockwise direction. So the value of spin quantum number, that is S, will be minus, it will be considered as minus half for this, right? So I have taken 4 examples, 4 different examples in which 4 different subcell has been taken S, P, D, F, and I have calculated 4 different quantum numbers for all the example. Right. Now I will discuss what is the shape of orbitals. Shape of orbitals. What is the shape of houses of the orbitals? What it may be, right? So S orbital, I am talking about S orbital. S orbital, it has spherical shape. S orbital. Can you tell me what is the direction of a sphere? Nothing, right? You cannot say that our sphere is present in the x direction or y or z. It is present in all the direction in the same way, right? So if someone asks you that does S orbital has any directional property? No. P orbital. Actually it is dumbbell shape. So 3 types of actually value, let me tell you. So for P subcell there are 3 possible orbitals, right? For P subcell, for P subcells there were 3 orbitals, that means 3 possible values, -1, 0, +1, 3 possible values. Okay, so there will be 3 possible direction. I have told you in the previous slide that M tells about the orientation, possible orientation of orbital that can be possible, right? So there are three possible values of M for there are three possible values of M for p orbital. So it will have three possible direction in space. That means if it is present in x direction, so we call it as px. If we will have y direction, it will be present in y direction, we call it as py, and we can say it as pz. Actually these are three axes, x, y, z, and our board is two dimensional. I am talking about three dimensional. So I can consider any line as any axis. So suppose I want to draw x, so I am taking it as, it is present in dumbbell shape, right? Dumbbell shape. I am taking it as x, it is as y, so it is py. So I am taking it as x, I can take it as right now as z, because it is x, it is y. Now z is must be here, but I can represent here at, I can write, I cannot write here, right? It is x, it is y, and it is x, it is y, and it is z, right? I cannot write here, it is two dimensional. Okay, so I have considered z axis here, right? If it is x, I can take any line as axis, initially x. If it is x, so to it 90 degree, from the 90 degree angle there will be y axis, and from it, both of it, at the 90 degree angle there will be z axis. It may be present here, it may be present here, right? Z axis, z, x, y, z, x by black pen, by blue pen y, or z by hand. So I have discussed about s orbital, p orbital, and now I am going to discuss the shape of d orbitals. See, d orbitals, they have double dumbbell shape. dxy, dyz, dzx, these are between the axes. If I take it as x, if I take it as y, so x, it will be minus x. If it is y, so opposite to it will be minus y. So whole this line is y axis. If I take it as the origin and I move to this direction, it is y, and if I move to this direction, it is minus y. I can take anywhere, I can take it as y here, I can take minus y here. So, but if I have taken y here, so I will take minus y this side, opposite to the origin, right? So it between the axis, that means it is present between the x and y. So x and y, x, y, x, y, x, y, x, y. So this is the shape of d orbital, right? dyz orbital. So if I take it as y, I am taking it as z. If it is y, so opposite to it, it will be minus y. Opposite to this, it will be z, minus z. So between the axis, that means y and z, yz, 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 between the axis, yz, yz, right? So now I take it as x axis, it as z axis, right? So now if it is x, it will be minus x, it will be minus z between the x z axis. xz, 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 right? So these three orbitals, actually there are 5 type of orbitals, because for dl is equal to 2 and possible values of m are 2l plus 1, so I am going to write here l as 2, so there are 5. So that's why 5 value of m, so because the value of m is 5, so there are 5 types of possible direction for the orbitals of d subset, right? So I have discussed the shape of 3 orbitals, dxy, dyz and dzx. Now I am going to discuss the direction of the shape of 2 more orbitals, that is dx square minus y square. It is between the axes. These are the, sorry, these were the between the axes, and now it is along the axis, along the axis, right? So if it is x, if it is y, so now I will make the shape of this orbital on the axis, right? X, it is also x minus x, right? Whole this line is representing x axis. Y, if it also, it is whole this line is representing y axis, so on y axis, right? So this is for x square minus y square. Now I am going to discuss last orbital, so listen carefully. As we have written dx square minus y square, we have to write dz square minus x square and dz square minus y square also, right? If we take over all of these 2 types of orbitals, then what will happen? dz square minus x square, listen, as I have written dx square minus y square, I will have to write dz square minus x square, I will have to write dz square minus dy square, and then I will take sum of these 2 orbitals, overall of these 2 orbitals, it will be dz square minus x square plus z square minus y square, z square minus square, z square minus y square, it will become d2z square, 2z square minus x square minus y square. I can write it as dz square minus x square by 2 minus y square by 2. I am going to divide by 2 in all these 3 axes, 2z square minus x square minus y square. If I divide here by 2, it will become z square from 2z square. If I will divide it by 2, it will become minus x square by 2, it will become minus y square by 2. Okay, it is like that. Now I am going to represent the structure of this orbital along the axis, right? Z square, it was a square, so we draw it on the axis. So we also, I am going to also represent it as on the axis, because it is as x square, z square, x square, y square. So now I am going to divide it by represent it on the axis. Suppose it is x, it is z, or somewhere there will be y axis, right? X, z, y. On the z axis, actually you can see that it is z square, but it is x square by 2, it is y square by 2. That means it will have the electron density on z axis also, but it will also have the electron density on x as well as on y axis also, but the value of electron density will be higher on z axis, lower for x and y axis, because it is 2z square, double of here, double of this, it is 2z square, right? 2 is the in the multiplication of z square, it is just x square and y square, right? So it will have electron density on this axis also, it will have electron density on this axis, y axis, which is like this, in this way. So I am going to represent it by this. Got it? So that's why the shape of dz square orbitals, it is like that. We generally call this orbitals dz square. But the representation, it is like that, dz square minus x square by 2 minus y square by 2. But we generally call it as only z square. If someone asks that dz square orbital has electron density along which axis, so you will say that along all the axes, x, y, z axis, the d orbitals has its electron density. Okay, it is like that. Now I am going to discuss some rules, some principles of Aufbau, Pauli and Hund rule. Aufbau rule. The meaning of Aufbau, to build up, right? To build up. So it tells that electron goes to that orbital for which value of n plus L is lower. Electron goes to that orbital for which n plus L value is lower. For example, we have two types of orbital here, 3p, 4d. So value of n will be 3, value of n will be 4, value of L sp. How we calculate the value? sp, d, f, 0, 1, 2, 3. These are the value of L. So for p, value of L is 1, 1. So n plus L is equal to 4. For this case, L is equal to, it is the value of n. For d, value of L is equal to 2. So n plus L is equal to 4 plus 2, that means 6. It is 3 plus 1, it is 4 plus 2, 6, right? So it has lower value, this orbital has lower value, 3p orbital has lower value of n plus L as compared to 4d. So it says that if electron has two opportunities to enter, then in this case electron will enter to 3p, not 4d, right? Suppose there is the value of n plus L is same for two types of orbital, then what will happen? If n plus L same, then electron goes to that orbital or subshell for which n value is lower. N value is lower. So what is the, suppose I take 4s and 3p, value of n is equal to, for this 4, value of n 3, value of L for this, for s orbital, for s subshell, value of L is equal to 0, for p subshell, value of L is equal to 1. So n plus L is equal to 4, n plus L is equal to 4, both have the same value of n plus L. In this case, in which orbital electron will enter? So this has the value of n as 4, this is having the value of n as 3, so this is the lower. So electron will enter to 3p. Okay, so we have calculated the value of n plus L for all the subcells, and we have managed in the increasing order of energy. So the order is like that: 1s, 2s, 3s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. So the value of electrons I am going to write here. 2 electrons are filled here, 4 electrons, 12 electrons till 3s2, 20 electrons for 4s, 38 electrons for 5s, 56 electron for 6s, 88 electron for this 7s, 5f, 6d, 7p, 8s. For this I am going to write 120. Suppose I want to write the electronic configuration. This helps in to write in the electronic configuration. If you want to write the electronic configuration, so we can write it in 5 to 10 seconds if we remember this flow of chart, right? Flow chart. So suppose I am going to write the electronic configuration for atomic number 23. So atomic number is given 23. I am going, that means there are 23 electrons, right? If it neutral, if it is neutral and the atomic number is 23, so number of electrons will be also 23. So I am going to write the electronic configuration for this. Electronic configuration. So see, 23 and 20 electrons has been filled till 4s2. 4s2, that means 20 electrons has been filled, right? Now I am going to write for 3 electrons, these 3 electrons, and 3 electrons will enter to this 3d, 3d. Okay. Suppose I want to write for z is equal to 60. That means if it is neutral, that means there will be 60 electrons. So I want to write the electronic configuration for 60 electrons, right? So electronic configuration will be 60. That means 56 has been filled till 6s2. Now there will be only 4 electrons will be left here. So 4 electrons will enter to this 4f4. So I can write electronic configuration in 5 to 10 seconds in this way. Now one more thing. Half filled and fully filled orbitals, half filled and fully filled subcells are more stable. There are 2 reasons for their stability. One reason is symmetrical distribution of electrons. Another reason is exchange energy, right? So half filled P, D, F or subcells will be stable. That means there may be maximum 6 electrons in P subcell. So P6 and P3 will be stable. D5 and D10 will be stable. F7 and F14 will be stable, right? So if we want to write the electronic configuration for chromium, which is 24, so it will be like as 24. So 4s2. It is representing 20 electrons, 4s2 representing 20 electrons. Only 4 electrons will be left. So I will add these 4 electrons in the 3d4. But as I have told you that half filled d orbital, d subcell is stable. So for the stability, 1s electron will enter to 3d subcells. So the final electronic configuration or the stable electronic configuration will be like that: 4s1 3d 5. And copper 29. Suppose I am going to write the electronic configuration for 29. So it will be like 4s2. That means 20 electrons has been filled. Now 9 electrons will be left, so 9 electrons will be in 3d subcell, but I have told you that D10 is fully filled, D10 it will be D10. It is more stable as compared to D9, so 1 electron will be shifted from 4s to 3d. That means the final or stable electronic configuration will be like this. I am going to tell you one more electronic configuration that you must know. Palladium 46. I want to write the electronic configuration for 46. See, 56 is higher, so I will take 38. That means I will write 5s. I will write 5s2. That means 38 electrons has been filled. 5s2, that means before it 38 electron has been filled. 5s2. Now I want to go to 46. So 46 minus 38, that means 8 electrons has been left. So 8 electrons will be added to this 4d. 8 electrons will be added to this. So for the stability, as D10 is more stable as compared to D8, so these 2 electrons will be transferred to 4d from 5s. So the final electronic configuration will be like this, 4d10, or we can write it as 4d10 5s0, or we can write it as 4d10 only, because there is no electron of in 5s subcell. Okay, it is like that. Now I am going to tell you about Pauli exclusion principle. It says that if we talk about one atom, there may be many types of electrons in that particular atom. So if we talk about that particular atom, so it says that no 2 electrons can have same value of quantum numbers. It says that each electron in an atom, each electron in an atom has unique set of quantum numbers. Okay, the set of quantum numbers cannot be same for 2 electrons in an atom, right? No 2 electrons can have same set of quantum numbers. Now I am going to discuss Hund's rule. It says that pairing will not take place. Pairing will not take place until all orbitals become singly occupied. Right. So these are the Pauli exclusion principle and Hund's rule. You can apply Pauli exclusion principle in any atom. You take 2 electrons in an atom and you find the value of quantum numbers. You will find that for these 2 electrons, the set of quantum numbers will not be completely same, right? It may be slightly different or it may be completely different, but it will not be completely same, right? Now I am going to tell you about some, right? So if it is a vacant orbital, orbital. We can say it as unoccupied orbital. If in orbital one electron is present, we can say it as singly occupied orbital. I can say it as half filled orbital. I can say it as unpaired orbital because there is no pairing. One electron cannot pair. For the pairing, two electrons must be there, right? It is said as fully occupied or doubly occupied, DOUBLY, doubly occupied orbital. I can say it as paired orbital. So it may make any confusion to you, so I have cleared it to you. So I hope that all the topics that I have discussed, you got all these points, right? I think you understand it well. If all of you have any doubt regarding these topics or about this chapter or about this class, you can ask in the comment section, right? Okay, so you can ask in the comment section. So bye, keep studying.